So let's proceed with more examples of integration by parts using the DI technique, which we introduced in the previous video. In this video I'll just do more examples. So I have 1 2 3 4 5 examples on my screen here that I'm going to try out. So let's start on the first one. Just pick a better color here. Alright, so that's the integral of x squared sine squared x dx. Just create a new page here. The integral of x squared sine squared x dx. So in the previous video we actually introduced this method of integrating by parts, the technique called the DI technique, and we said the first step to use this is to actually draw a table. So let's go ahead and do that. Then we have d in one column, we have I in another column. So we choose one of these functions which can be differentiated up to 0, and the other which is easier to integrate. So in this case x squared is easier to differentiate up to 0, so I write x squared here. Alright, so if I differentiate x squared I get 2x. If I differentiate 2x I get 2. If I differentiate 2 I get 0. So once we see the 0 we stop at that point. Let's also integrate now sine squared x, but as you understand sine squared x is difficult to integrate when it's like this, so we've got to change this into something else, maybe a double angle. So this we have to modify it into a double angle. We can express this in terms of cosine. Luckily I'll show you what that is. So we know that cosine of 2x is cos squared x minus sine squared x, but we can substitute, we can replace this here. So I'll have cos 2x, we can replace cos squared x is 1 minus sine squared x. We've got this trig identity that cos squared plus sine squared x equals 1, so I can substitute for that, then minus this sine squared x. So cos 2x is 1 minus 2 sine squared x, and if you make sine squared x the subject, it turns out that sine squared x is actually a half into, oops, need a bracket here, half into 1 minus cosine of 2x. So I can just write this as a half minus a half cos 2x. Now instead of writing sine squared x in this column, I'll actually write that. I'll write a half minus a half cos of 2x, because that's easier to integrate. We know how to integrate these terms, but we don't know how to integrate sine squared x when it's like this. Alright, so this is much better. So if we integrate this, we'll have a half times x minus that's going to be a quarter. When we integrate if we integrate cos 2x, we actually differentiate this and we get a 2, and we write that as a half. So a half times a half gives us a quarter. The integral of cosine is sine, so that gives us sine 2x. Let's do that 2 more times. If we integrate this, we have that's a half. Okay, I think that's going to be a quarter. Let me write that better. That's a quarter x squared for obvious reasons. This is to power 1. If I increase the power by 1, that becomes x squared. If I put that power down here, that will become a quarter minus, alright, this is going to be 1 over 8. Well, the integral of sine is negative cosine, which makes this plus cosine 2x. Alright, one more time, this is going to be 1 over 8 x squared Let's see what we have here. The integral of cosine is negative sign, so this is going to be a minus 1 over 16 sine 2x. Alright, we're almost there. Let's put signs here, plus, minus, remember, alternating positive and negative signs. Then we multiply the adjacent rows or columns. I don't know what that is. So we can now write out our final solution. The integral of x squared sine squared x dx is going to be a little longer. So x squared times this, that's going to be x squared into a half x minus, that's a quarter, sine 2x. Alright, negative 2x, okay, you multiply that with a quarter of x squared minus 1 over 8 cos 2x. Alright, then what else? Plus 2 times this, plus 2 times 1 over 8 x squared minus 1 over 16 sine 2x plus a constant of integration, obviously. So actually I've run out of space, but this can be simplified further, so let me just do this. Alright, so if I multiply these terms inside, that's going to be x cubed over 3, over 2, that's 2 here, okay, sorry about that, minus x over 4 sine 2x minus, that's going to be a half x cubed minus, that's x over 4 cos 2x. Alright, here we are now, plus x squared over 4 minus 1 over 8 sine 2x. I guess this is actually plus, yeah, negative 2x times negative 1 over 8, alright, plus c. So let's try to collect like terms. I'll create more space, just a little here. So let's look at x cubed. We have x cubed over 2 and this, so these ones actually cancel out. Alright, so we have terms containing sine 2x. Alright, we have this term here and this term here. Okay, I'll come back to those. Let's begin with this term here, x over 4. Of course, you can write in any order. I'll first take off this. So I have x over 4 minus, that's not x over 4 cosine of 2x plus x squared over 4 minus x over 4 sine 2x, that's the first thing here, then minus 1 over 8 sine 2x plus a constant. Yeah, you can actually go on and simplify this, but I'll just stop here for now. The basic idea is, as long as you can see how we actually go about this using the DI technique. It's really a long one, but yeah, the DI method helps us to make it a little bit shorter and easier to integrate. So let's look at some of the other examples. So go back to the previous page. So that was x squared sine x sine squared x. Let's work out this x tan squared x. So I'll just have to delete all this page. Okay, so problem number 2x, that's just x tan squared x. Guess that's it. Alright, so we draw a table, D on one column, I on the other column. You can obviously see that here x is differentiable up to 0. So if I differentiate x, I get a 1. If I differentiate 1, I get a 0. The integral part, if I integrate now, tan squared x cannot be integrated, but we are lucky that tan squared x is sec squared x minus 1. So instead of tan squared x, we'll just write here sec squared x minus 1, because we can integrate both of these terms here. So if we integrate this, we'll get the integral of sec squared x, that's tan x. The integral of 1 is x. Alright. Okay, one more step. The integral of tan x, that's the natural log. I'll just show you this in a moment. The integral of tan x dx is actually the integral of sine x divided by cos x dx. Now you notice here that the numerator is a derivative of the denominator, so that's negative natural log of cos x. It comes from the fact that, I'll show you this, if you have the, maybe here, if you have an integral of a function looks like, if a function looks like this, such that the numerator is actually the derivative of the denominator, then that's always going to be the natural log of the denominator, as you can see here. So the derivative of cos x is negative sine x, so that's why I put the negative here just to account for that. And so we end up with this negative natural log of cos x. Alright, so I'll come back here and write this negative natural log of cos x minus x squared over, okay, the integral of this is x squared over 2. Alright, we're almost there. Let's put signs here. This is plus, minus, plus. Those are alternating signs, beginning with a positive, don't forget. Then we multiply this. So the integral of x tan squared x dx is going to be, so x times this, so I'll have x into tan x minus x, then minus 1 into the negative natural log of cos x minus x squared over 2, plus a constant of integration, obviously. So you could expand this. Here I have x tan x minus x squared plus the natural log of cos x plus x squared over 2 plus a constant. Maybe just one more step here to simplify this. That would be x tan x minus, so this minus x squared and plus x squared over 2, that's minus x squared over 2 minus x squared over 2 plus natural log of cos x plus a constant of integration. So that's our final solution to this. Alright, again you can see the DI method really makes this shorter. Okay, I'll just go back to the previous page to see. Okay, question number 3, we have the integral of x exponent negative x times e to the x. Alright, that looks shorter, so I'll erase this page. That's problem number 3, x times exponent of x dx. Okay, using the DI method, so I draw a table. I put D on one column, I on the other column. You can already see that x is easier to differentiate up to 0. So I write x in the D column. Let's differentiate x, we get a 1. If we differentiate a 1, we get 0. Alright, e to the x in the other column. If I integrate this, it remains e to the x. If I integrate it again, no change. the signs here, positive first, negative, then positive, and so on if we had more columns. Then before we actually do the final step, we multiply the adjacent columns like that. Of course, taking these signs into consideration. So my integral of x exponent x dx is going to be positive x times exponent x, that's x exponent x. Then we've got minus 1 times exponent x, that's minus exponent x, plus constant of integration, and that's our final solution for this. Yeah, this has been pretty short, which is nice. So let's look at which other problems we have. Problem number 4, yeah, this looks interesting also. The integral of x times 2 to the power x dx. Okay, so I will erase this page. Problem 4, x times 2 to the power x. Let's draw our table like we've been doing. So we have d, we have I. You can already see that x is easier to differentiate up to 0 in this case. So if I differentiate x, I think I need to make this column bigger for reasons you will see quickly. So also I get another color. Alright, so I have x. If I differentiate x, I get 1. If I differentiate 1, I get 0. We stop there. Then let's have 2 to the power x here. If I integrate 2 to the power x with respect to x, we get 2 to the power x divided by natural log of 2. I actually have an independent video where I talk about how to integrate this and examples similar to this. I'll leave a link to a video in the description where you can see that. But for this, so we have 2 to the power x divided by natural log of 2. If we integrate this again, we'll have okay, that's going to be 2 to the power x again divided by natural log of 2, all this squared. Alright, one more step. We have to put signs here, plus, minus, plus, alternating signs, plus and minus, beginning with plus, and then we multiply the adjacent columns. And finally, the integral of what's that? X times 2 to the power x dx is going to be, so we have positive x times 2 to the power x divided by natural log of 2. That's x times 2 to the power x divided by natural log of 2. Then minus 1 times all this. So we have minus 2 to the power x divided by natural log of 2 squared. I guess you can actually factorize out this. Oh, that should be plus a constant of integration. So I factorize out 2 to the power x divided by natural log of 2. What do I have inside the brackets? That's x minus 1 over natural log of 2. If that helps, plus a constant of integration, and that's our final solution for this. Alright, so that looks awesome. Alright, again you can see how useful and short the DI method can be. And we have just one more problem to go. That's the integral of x exponent negative x. Let's try to do that first. I'll clear up this page. Problem number 5, the integral of x exponent negative x. This is similar to problem number 3 that we've just attempted. We have d and I. X is easier to differentiate. In fact, if we differentiate x, we get 1. If we differentiate 1, we get 0. Then we have exponent negative x. If we integrate this, we get exponent negative exponent negative x. If we integrate that again, positive e to the negative x. Have alternating signs here, plus, minus, plus, and so on. Multiply the corresponding columns, so the integral of x, exponent negative x, I should have said here with respect to x, that's going to be x times negative exponent negative x, that's negative x, e to the negative x, alright, minus 1 times this, that's minus e to the negative x, plus a constant of integration, and there we have it. Alright, thanks for watching this video. If you like this video, give me a thumbs up. Also subscribe to the channel for more content like this. In the next video, which is I think the final video, where I talk about the DI method, I'll take on even more interesting examples where we have the original integral reappearing, especially if you have exponential functions together with trigonometric functions in one integral. Alright, see you then.